All right, so now let's look at a few example calculations using this v equals f lambda equation, as well as a few of the other equations and calculations I've already showed you. So let's go to this one. It says the speed of a transverse wave in a string, so we have a wave being made in a string, is 15 meters per second. So the wave is traveling from one end to the other at a speed of 15 meters per second. The source of the wave produces a disturbance that has a frequency of 5 hertz. What is its wavelength? All right. Again, all of these problems are going to be made much, much easier if you roll through the guess method, right? You can either define what you're given over here, or you can just look at the problem itself. And let's look at this. This is speed. I'm going to just write that right on the problem. If I'm doing my givens, right? V equals 15 meters per second. You understand all that. Hopefully you understand how to do that at this point. I've done that quite a bit. 5 hertz is our frequency. And then it wants to know what is its wavelength, right? And remember, in order to do this stuff, you got to know the variable. So we got to start to memorize that the variable for wavelength is lambda, that funny looking Greek letter that looks like a little broom. So we need lambda, we have v, we have f, and then obviously you've probably figured that out at this point. V equals f lambda is the equation that has all those things in it. Now we've just got to plug the numbers in and solve. Our v is 15. Right? Really bad 5. I'm sorry about that. Let's redo that. It's a little bit better. Frequency is 5, and we have lambda. To solve for this, hopefully you figured out all we need to do is divide by 5. 15 divided by 5 gives us a wavelength of 3 meters. Pretty simple and straightforward, right? Not that big of a deal. Let's go ahead and look at another one. A wave with a frequency of 20 hertz, there's our F, there's our frequency, travels along a slinky. So now we have a slinky wave, and this happens to be a compression slinky wave. If the distance between successive, listen to this, if the distance between successive compressions is 0.4 meters, what is the speed of a wave? Some people have trouble with this one because they don't know what this is. But if you know the definition of wavelength, you know that that's what this is. The length of the wave is the distance between successive parts of the wave, the distance from one part of the wave to the next identical part of the wave. And in a compression wave, that's compressions. We can measure the distance from one compression to the next, and that would be our wavelength. So they're giving us lambda here. They're giving us the wavelength, and they want to know v. What is the speed of the wave? Once again, v equals f lambda is our guy, and let's plug in numbers and solve. This one gets super easy. All we have to do is multiply if they're asking for speed. 20 times a wavelength of 0.4. 20 times 0.4 gives us 8. So 8 meters per second is the speed based on the frequency and the wavelength. That's how fast this wave is moving. The slinky itself isn't moving, remember, doesn't carry matter, but the slinky wave is moving at a speed of 8 meters per second. All right, let's move on to another one that actually brings in some other parts as well. So we have a sound wave that has a frequency of 262 hertz and a wavelength, lambda, of 1.29 meters. That's the information we're given. And there's going to be 3 questions we're going to look at here. We want to know the speed of the wave. We want to know how long it'll take the wave to travel the length of a football field, sound wave. And we want to know the period of the wave. Let's go each of those in turn. Actually, right now, why don't you go ahead and just pause this video and see if you can do these 3. And if you can't figure one of them out, that's okay. Go to the next one. Do as many as you can. Go ahead and pause the video right now and see if you can figure that out. Okay, the first one, the speed of the wave, should be the easiest one. We've already done one exactly like this a minute ago. That's our v equals f lambda equation because we have f and lambda. Our frequency is 262 and our lambda is 1.29. If you multiply those two together, hopefully you got a speed of 338, approximately 338 meters per second. You should remember that number because that's the speed of sound. We're going to look at the speed of sound later when we get to sound, but right now you don't have to know that. We're actually going to use 340, but it's pretty close to 338. So that's the speed of our wave. That's how fast the wave itself is moving, not the molecules in the medium, not the air. That's how fast the wave is moving from one place to another. Given that speed, we want to know how long it'll take the wave to travel the length of a football field. Now, people understand that this 91.4 right here is some length, and sometimes they'll say, well, that must be the wavelength, and it's not. Because we already know the wavelength. This is the same sound wave we're talking about. Wavelength is 1.29 meters. We already know that, and this is way different than 1.29. There's no way, by the way, there's no way a sound wave has a wavelength of 91.4. That's way too big. Well, what is that? Well, we actually have to go back to another equation that I haven't introduced to you because we did it already. Actually, at the very beginning of the year, even if you weren't in my class, I know you did this equation, and it's the good old speed equation that looks like this. V equals d over t. We know the v, that's the speed of our wave. How far is this wave going to travel? Well, that's what this is. That's the simple distance we want the wave to travel. I can change that distance. How long will it take it to go 2 football fields? How long will it take it to go a mile? Whatever it is. And then how long is the time is what we're solving for right there. Now, this is an important equation to know. We're going to use this again when we get to sound. I just wanted to introduce it here because this is actually what you do. I know everybody's done this. When you watch a storm and you see lightning and then you hear the thunder. By the way, in case you didn't know, thunder is the sound of lightning. Some people don't know that. But if you count the number of seconds between the lightning and the thunder, you can actually calculate how far away the lightning has struck, how far away the storm is, by basically using this equation as long as we know the approximate speed of sound in air. This is going to be a little bit different. Now, instead of calculating the distance, we're going to calculate the time. Let's go ahead and plug these numbers in. Our V is 338. It's going to go in here. Our distance is 91.4. And we are solving for time. Now, this is the most common algebra mistake I get. If you're solving for the variable in the denominator, most people don't know what to do. They'll divide here, they'll multiply here. One thing to help you is, let's use some common sense. Let's imagine what's happening here. You're standing on one end of a football field, you have a friend standing on the other, and they're going to yell or clap. How long is it going to take you to hear them? Probably not long, like less than a second. How do we get a number for time that's less than 1? Well, we have to divide by something that's bigger on the bottom. We have to divide by something that's bigger than the number on the top. Well, the way we do this algebraically is we have to get rid of this variable. If you're solving for the variable in the denominator, it's got to come out first. And the way to get it out of the denominator is to multiply by it on both sides. Multiplying by that variable simply gets rid of it here, and it puts it over here on this side. So now we have 338t equals, we've gotten rid of the t over here, we have 91.4 left. We have a brand new equation. Same equation, but it's rearranged. Now it's a lot easier to see what to do. We're going to divide by 338 on both sides. Gets rid of it over here. 91.4 divided by 338. If you do that, let me make sure I remember what this was. 91.4 divided by 338, 0.27. And that, if you think about it, should make sense to you. It takes about 1/3 of a second for that sound to reach. Let's go back. If you mess this up and you divide by 91.4, 338 divided by 91.4 will give you 3.69 seconds. That doesn't make sense. There's no way that the sound from one end from a football field to the other would take almost 4 seconds to reach you. It's way too long. Doesn't make any sense. It takes some time, but not that much, right? So that's what I talk about with common sense. That's what I mean. So we got the speed of the wave. We know how long it'll take to go the length of a football field. And now we want to know the period. Now remember what period is. Period is the amount of time it takes for one wave to happen, or one cycle, or one oscillation of that sound wave. And this is a sound wave. It's an air molecule. How long does it take that air molecule to go boom, boom, boom? One time. Not very long. Now, if we had a time and a number of waves, we could do this, but we don't have that. What we do have is the frequency. Remember, period and frequency are very closely related. As a matter of fact, they're inversely related, and they are inverses of each other. So to calculate the period here, all we have to do is 1 over the frequency. 1 divided by 262 gets plugged in right here. And that, as you can see, is going to give us a very small number, 1 over 262.0038. And we can leave that right there, 0.0038 seconds. If you want to move the decimal and sound really cool about it, we could say 3.8 milliseconds, right? But you don't have to know that. You won't be required to do that on any tests or quizzes, all right? So these are some examples for the wave equation, as well as this wave speed using distance and time.